So just to recall what we have done last time, we have considered the transition from discrete systems in classical mechanics. That means systems with finite number of degrees of freedom, the transition to continuum when the number of degrees of freedom becomes infinite. And in the process, it was very natural to introduce the concept of a field, namely the function which represents dynamical degrees of freedom, function which depends on the coordinates, on the space point, and also on time. And so today, what we will do, we will slightly develop this concept further, the concept of the field. And then we come to the discussion of very important symmetries of quantum field theory, which is a Lorentz symmetry and its further generalization, Poincaré symmetry. Okay, let me now then stop my video. And if you don't have questions concerning the material of the previous lecture, I will start the discussion of new stuff. Okay. So the concept of a displacement field can be further generalized to the case of multidimensional systems. For instance, in 2 dimensions, we may consider two-dimensional lattice of strings. So we have our masses now in this way, for instance, equidistantly placed on a 2-dimensional plane with coordinates x and y. And these masses will be connected by springs like this. And then what we do, we allow for longitudinal fluctuations of these masses in the 2-dimensional plane connected by these springs. And in this case, a very natural quantity to discuss is a displacement field phi, depending on coordinates of a point at the equilibrium. These coordinates I will denote by I and j. So I and j are discrete coordinates specifying the position of a given mass at the equilibrium position. Say this will be I and this will be j. And then the displacement field in this case is a 2-dimensional vector because particle now can move in 2 dimensions. So naturally, the displacement field is a 2-dimensional vector. And approximation, the continuum approximation of this system is what is called membrane. And what we are studying then in this case is longitudinal fluctuations of this 2-dimensional membrane. Then further on, what you can do, you can go in 3 dimensions, and you can imagine that now you have a system of these oscillators in 3 dimensions, naturally connected again by springs. Okay, like this. And therefore, now we will be studying in this situation the fluctuation field, displacement field, which is a 3-dimensional vector, depending on the coordinates a, j, k, specifying the position of a particle in the equilibrium. Now, doing absolutely the same derivation as we have done just for the case of 1-dimensional displacement field, at the end, we will end up with the following differential equation, which describes the evolution of this, in this case, a 3-dimensional vector. Namely, any component of this vector will undergo the following dynamics. So double dot here on phi means the second time derivative. Then there will be coefficient C1, second derivative in the direction x of this vector phi. Then there will be C2, second derivative in the y direction of phi minus C3 derivative in the z direction of phi, but also there will be cross derivatives, C4, say dx dy acting on phi minus C5 d say x dy dz acting on phi, and then minus C6 dx z acting on phi is equal to 0, where these coefficients C1 from C1 to C4, to C6, they encode the properties of our solid. They are like similar to propagation velocity we have seen for the case of the one-dimensional solid. What we also see that many quantities which appear in this description are fields depending on space-time variables, and these fields depending on space-time variables behave themselves as tensors. So they are tensors. Tensors, or more generally, tensor fields. So tensors and tensor fields. Tensor fields. And therefore, it makes for me very natural to discuss and introduce and discuss the concept of a tensor field from the very beginning. So, as you know, tensors in any coordinate system represent a set of numbers. Which transform by changing, or when changing one coordinate system to the other in a definite way. For the tensor fields, we are asking about transformation of this set of numbers under general coordinate transformations. So consider a transformation of coordinates of this type, x mu, just a second, let me delete this, x mu goes to x mu prime, depending on x mu. Such transformations we assume to be invertible, and these transformations belong to the class which we characterize as general coordinate transformations, and we will assume that we are working in d dimensions, so the coordinates mu, the index mu nu of our coordinates run from 1 up to say d. Then a tensor field phi with indices mu1 and so on, mu p, nu1 and so on, nu q, is a tensor field of rank pq. So this object depends on the point x. If under general coordinate transformations, it transforms in the following way. In the new coordinate system, it is described as phi prime, depending on coordinates mu1 and so on, depending on indices mu1 and so on, mu p, nu1 and so on, nu q. On x prime equals to dx prime mu1 over dx lambda 1 and so on, dx prime mu p over dx lambda p, dx rho 1 dx prime nu 1 and so on, dx rho q over dx prime nu q, and phi on lambda 1 and so on lambda p, q1 and so on rho 1 and so on rho q on x. So under general coordinate transformations, the tensor field phi of rank PQ is an object which under general coordinate transformations is transformed in the way I'm writing here. So here over indices lambda 1 and so on lambda rho, there is a summation. And the same is also about indices rho 1 up to rho q. We sum over these indices. So I'm using here Einstein convention about summation of indices, so I'm not writing explicitly the symbol of summation, but you have to have in mind that what I'm doing here, I'm summing using this standard Einstein convention about summation of indices. This is how tensor fields transform under change of the coordinate system. As you see here, the matrix dx prime with index mu over dx, say lambda. This is a matrix with indices mu, say mu lambda. And this matrix is known as Jacobi matrix. This matrix is non-degenerate, and therefore it's an element of the group GL R, or D, let's write dr. D means dimension, and R means that this is a real matrix, matrix of real numbers. So this group GLDR is a group of all invertible, a group of all invertible D by D matrices. D by D matrices.
What you said about D?
D is simply dimension, which is an integer number. It can be 1, 2, 3, and so on. It's a dimension of our manifold on which we define our tensor field. Okay?
Okay.
D is just a number, integer number, positive integer number, which specifies the range of the coordinates mu, lambda, nu, and so on. They are running from 1 to D, specification of the range of indices mu, nu, and lambda, and so on. And so these are tensors. These are tensors, and further restrictions on possible transformations of coordinates can be imposed by physical requirements. For instance, if you are talking about the Galilean invariance, then you restrict the general coordinates transformations to that of the rotation group. You are saying that this transition from x to x prime is a rotation in this case. Analogously, if you would like to implement Einstein relativity principle, which allows only for Lorentz transformations, then in this case, you restrict the general coordinate transformations to that of Lorentz transformations, which we will be discussing now. And in this case, people are talking about tensors on a Lorentz group or tensors on rotation group, and so on. So once again, the group of possible transformations can be restricted by extra physical requirements of your problem. A simple example, of course, of a tensor is given by a scalar field. Scalar, in this case, is an object which transform under general coordinate transformations according to the formula phi prime on x prime is equal to phi on x. The scalar field does not have any indices, and therefore the Jacobian matrices do not appear. It's a tensor of rank 0, 0, so no indices. And then the transformation rule for the scalar field is given by this formula. So it's sort of important to realize that physically the points, there is only one point, but in different coordinate, and this point is described in one coordinate system. It's specified by the coordinate x, but from the point of view of the other coordinate system, it has coordinate x prime. But physically, this is a one and the same point. And then the scalar field is a function which, under the change of coordinates, behaves itself in this way I'm writing here. So that's the definition of a scalar field. So be careful. So scalar field is not something which behaves like phi prime on x is equal to phi on x. This is not true. This is not a scalar field. Well, you can see it. For instance, if you take a function, say any function you can imagine, say for instance, if you take sine x, and then you make a coordinate transformation, like for instance, x goes to x prime squared, then what you will see here, you will just substitute x for x prime, so you will get sine x prime squared. But of course, now you realize that what is written down here is not the old function depending on x prime, because if I would write phi on x prime, then it would be a sine on x prime. So it's kind of a new function on x prime, and that's why we are writing here phi prime on x prime, meaning that the form of the function itself changes. Because it's a function, as a function of x prime, it's a different function. It's not sine on x, but it's sine on x squared. So the form of the field itself changes as well under this transformation. That's why this transformation law for scalar has this form which I'm writing here. But physically, x and x prime describe the one and the same point, which in different coordinate system has different coordinates, x and x prime. Okay, that is a remark which I wanted to make about tensor fields, because tensor fields in general will appear in our discussion of quantum field theory very often. Next to the scalar field, of course, there is a vector field which carries just one index up. And an example of a vector field would be a velocity, for instance. Velocity vector is a vector, and you can make it also a vector field. For instance, if you discuss in hydrodynamics the flow of a liquid, then you need a tensor field of velocities of volume elements of this liquid, and then it would be natural to use the tensor field of velocities, or vector field of velocities in this case. You can also have an example of a covector, which means tensor with a lower index. This would be a gradient of a function. Gradient of a function would be an example of a covector. And more generally, you might have, for instance, a metric on a manifold. This would be a tensor with two lower indices, and so on. So we will see in the development of the course further examples of tensor fields. And now I would like to return back to the action principle in general. So action principle, as we have already discussed last time, plays an important role in describing of dynamics. So action principle and Euler-Lagrange equations. And in general, what we mean by this is that we deal with a functional S, which is a functional of field phi, and it has the following form. So it's an integral over dx of the Lagrangian density which in very general terms might depend on X, collection of fields phi I, and on the first derivatives, d mu phi I. Here, in general, dx I will write as a measure which corresponds to, or which is by definition, is product of dx0, dx1, and so on, dx, d minus 1. So I assume that I'm considering such objects on a d-dimensional space-time, where x0 signifies the time direction. So x0 is c, speed of light, multiplied by t. And the other directions, x1 and so on, d minus 1, they are spatial directions. So action is an integral over d-dimensional space-time coordinates of the Lagrangian density, which is considered in general to be a function of x, fields phi I, and their first derivatives. And this is a most general theory. In a sense, you may ask yourself why I'm considering here only first derivatives. And this is because I want to consider non-degenerate, or what is called unitary theories, where equations of motion, which I will be deriving from this action, contain only second derivatives in time of the field phi, and second derivatives in the spatial directions, but not high derivatives. The theories with high derivatives of the field phi, they are much more complicated, classically and especially in a quantum theory.
Is there an example of such a theory?
Yes, that is a very natural generalization of the Newtonian mechanics, because in Newtonian mechanics, you know that equations you are deriving, these are second order equations in time, which means that to specify the trajectory of a particle, you need to specify the initial coordinate and initial velocity and nothing else, right? So initial coordinates and initial velocity are enough to solve the Cauchy problem for such a dynamical system. And we would like to extend this principle, natural principle, which we observe in nature concerning our world, I mean Newtonian dynamics. We would like to inherit this principle also for the field theory. That's why we are requiring that our equations of motion derived from this Lagrangian contain only second order derivatives, but not higher derivatives. So we still want to have a unique solution of the Cauchy problem in a sense of given standard initial data, position of the field at the initial moment of time, and the velocity in the initial moment of time. Then the Cauchy problem will have a unique solution. So we are propagating this principle, or we are inheriting this principle from the standard Newtonian mechanics. We want to somehow to implement it also for our fields. And further on, what I will also require, I will require that there will be no explicit dependence on X. So all dependence on X will come only through the fields phi and its derivatives, but there will be no explicit dependence on X. Okay. Now the index I here will have double meaning. It will combine simply labels of different fields, when I will be talking about fields of different nature. And also it will be a uniform label for all possible tensor indices of one field. Because here you may consider the Lagrangian not only for a scalar field, but for instance, Lagrangian for a vector field, as you do, for instance, in electrodynamics. You know, you have electromagnetic field. Electromagnetic field is a vector. And that's why it carries a space-time index. And by index I here, for instance, you might mean the index of a vector of a one vector field. But you may also mean a collection of scalars by index I. And in general, you might have tensors of arbitrary rank, and you have many of them. And that's why index I here stands for the universal description of these possibilities. Okay, so from this action, you derive equations of motion by using the principle of the least action. And this is a standard thing. In fact, we have already seen an example how this is done by means of variational principle or by means of principle of the least action in the last lecture. In any case, what you derive from this action is what is called variational derivative. And this variational derivative is variation of the action with respect to variation of the field phi. And this comes out as a derivative of the Lagrangian density with respect to the field phi I minus d over dx mu, derivative of the Lagrangian density with respect to d mu phi I. And this object here, if we set it to 0, then this is what we know as Euler-Lagrange equations. Euler-Lagrange equations. And solving the Euler-Lagrange equations, we find the actual dynamical trajectories of our system. Now, what you can do also, you can just differentiate this Lagrangian derivative with respect to x mu in an explicit way by taking into account that Lagrangian density is a function of phi and its derivative. So you can write for this Lagrangian derivative epsilon I is the following expression. So dl over d phi I minus second derivative of Lagrangian density with respect to d phi I, let me write here, comma mu, d phi j, and here phi j, comma mu, minus second derivative of the Lagrangian density, d phi I, comma mu, d phi I, comma mu, d phi j, comma mu, phi j, comma mu mu. And this is by definition, phi I, comma mu is a derivative of phi I with respect to x mu. This is how these equations are written in the full glory. Here you see the second derivative of phi with respect to x mu and x nu. This is how Euler-Lagrangian equations look like. Now it is important to realize that in fact Lagrangian is not uniquely defined, which leads to the one and the same equations of motion. So you can have different Lagrangians which lead to the one and the same equations of motion. And this is because we can always change the Lagrangian density by adding to it the total derivative of the form d mu lambda mu, where lambda mu is considered as a function of the field phi, or the fields phi I. But not of their derivatives, because if you also assume that this lambda mu depends on the derivatives of phi I, then since here you see the second derivative, you see the derivative of lambda mu, then would lambda mu depend also on derivative? Let's write nu of phi I. then such an addition would lead to the appearance of the second derivative of phi in the Lagrangian, and this is something which we have prohibited because we require that our Lagrangian depends on the first derivative of phi. That's why if you don't want to change this nature of the Lagrangian to depend only on the derivative of the field phi, then you assume that lambda mu depends just on the field, but not on its derivatives. Okay.
Can you explain this part one more time, this last part?
Last part, what I'm saying is that, yes, I have not yet finished the explanation. Maybe it will become clear in a moment what I mean. I'm saying that if you change the Lagrangian by adding to it the total derivative of the form d mu lambda mu, where this vector lambda mu is a function of the fields phi I only, then equations of motion will not be changed. So this transformation, let me write down this transformation does not change or does not influence equations of motion, which are the same as Euler-Lagrange equations.
Well, thank you, sir.
And then I said that I require that this lambda mu depends only on the field phi, on the fields phi I, but not on their derivatives. And this is because I want my new Lagrangian, which now contains this extra total derivative, to continue to depend only on the first derivatives of the field phi, because this differentiation here, external differentiation by d mu, will now produce the first derivative of the field phi I. But would it be there already the dependence on the derivatives of phi I, then this external derivative here, d mu, would produce higher derivatives of phi I, and then the new Lagrangian will not depend only on the first derivatives of the field, but also on the higher derivatives. And this is something which we would like not to have. Now, why it is so? Why the equations of motion will not be changed under such addition? This is because if you now look at d mu lambda mu term, you see that this you can write as a derivative of lambda mu with respect to phi. Let's consider the case when we just deal with one scalar field, with just a single field, and not necessarily scalar, just on a single field phi. And then this derivative d mu lambda mu can be written as a derivative of lambda mu with respect to phi, and then derivative of phi with respect to mu, like this, like you differentiate a composite function, right? And then you may trace how under this addition the Lagrangian derivative changes. So we know what Lagrangian derivative is. It is given by this expression here. So now to see how this derivative changes, we can substitute instead of Lagrangian in this formula this additional term and see what happens. So this means that our derivative, Lagrangian derivative, will get an extra contribution depending on lambda. So let me maybe write it in this way. It's better to write it like this. So Lagrangian derivative will go to Lagrangian derivative plus extra contribution depending on this lambda. And this extra contribution depending on lambda will be given by d over d phi on d lambda. Let's write it with index lambda here over d phi d lambda phi. This is this term here is a first term we have in our Lagrangian derivative, where instead of Lagrangian density, I substituted this extra contribution. And now I have to subtract the second term, this one here, also substituting instead of Lagrangian this total derivative. So this would mean, if I write it explicitly in the open form, as second derivative of d phi, let's write derivative with respect to mu in this way. So phi comma mu, and then d lambda lambda over d phi comma lambda, like this, multiplied by phi comma mu. This is the first term here, this one, in the open form. And now the last one will be a second derivative, d phi comma mu, d phi comma nu, multiplied with d lambda lambda over d phi comma lambda, and multiply with the second derivative of phi with respect to mu and mu, x mu and x mu. And this must be equal to 0. I mean, the whole thing must be equal to 0, but you can see that this additional contribution is 0 by itself. How do you see that? Well, first of all, if you will be looking at the last term here, you see that this object depends on phi, and here you have the first derivative. And so if you will be differentiating what is in this bracket with respect to derivatives, since you have here two derivatives, the result of this differentiation will be 0. Because what is in the brackets involves the first derivative of phi only once. And that's why this term is 0. While these two terms, they just cancel each other. Again, if you open the brackets here, then you will see that this will be just second derivative of lambda with respect to phi, so like this, multiplied by phi comma lambda. This is what is written down here. Can be written as a 5 comma lambda. And here, one derivative with respect to phi will be acting on this term, which will produce contribution of this type, while the derivative with respect to mu will be acting on the derivative with respect to lambda. It will produce a Kronecker delta d lambda mu. Then you sum up over lambda, and you will get d lambda over d phi with index mu, and multiply by phi prime mu. That's exactly the term here, and they are with the different signs, and so that they cancel each other. And so the contribution to the Euler-Lagrangian equations from this total derivative term is actually 0. So this additional term does not contribute to equations of motion. Okay, that is...
So we can say that it's a gauge invariant.
Say it again, sorry.
So it's a gauge invariant thing.
It's not gauge invariance. It's just, in a sense, it means, it's just an invariance of the Lagrangian, which does not contribute to equations of motion at all. So equations of, it's like a topological term you may add, which does not influence the dynamics at all. Equations of motion, in a sense, absolutely do not see the presence of this term. It changes nothing concerning the dynamics. It just tells you that if you would like to implement variational principle, and this means that you have to talk about Lagrangians, action, and Lagrangian densities, then these quantities admit a more, how to say, general class in comparison to equations of motion. You might have different Lagrangians which differ from each other by this total derivative term, which nevertheless lead to the same dynamics, leads to the same trajectories. Okay. Now, after these general remarks, which we have to have in mind when we talk about the Lagrangian formalism, I will come to the discussion of Lorentz and Poincaré groups. So Lorentz and Poincaré groups. Now, as I already mentioned in the first lecture, symmetries play an extremely important role in our description of nature, in our understanding of nature. For instance, translational symmetry implies that if we know physical laws at one space-time point, then we know them at any other. And which means that, in fact, the physical laws are not random from point to point. And similar remarks, of course, concern also, for instance, rotational symmetry, which means that laws in different directions can be related to each other. And among possible symmetries, there is one which has a universal character, far from stars. Far from stars. And this is Poincaré symmetry, which combines Lorentz symmetry or Lorentz transformations with shifts of space-time coordinates. And from mathematical point of view, these transformations have a structure of a Lie group. A Lie group. And so to recall, let me start probably, I need to recall the notion of a Lie group. And to start with, let me first say what is a group. So a group G, is a set of elements of any nature, which satisfies the following set of axioms. Which satisfies the following set of axioms. First, for any two elements, G1 and G2 belonging to our group G, one can define their product, G1 dot G2, which also belongs to the group. And this product satisfies the associativity condition. So the product is associative, which means that it does not matter how you put the brackets. First, you multiply G1 with G2 and then with G3, and it should give the same result if you first multiply G2 with G3 and then you multiply this with G1. Associativity. Second, there exists a unit element belonging to the group, such that G multiplied by E is the same as E multiplied by G is equal to G. A unit element, or identity, we call it sometimes identity. And the third very important axiom, or very important requirement, that for any element G from the group, there exists an inverse. There exists an inverse element G minus 1, such that G multiplied by G minus 1 is equal to G minus 1 multiplied by G is equal to E. So this is the definition of a group. And now an important class of groups constitute Lie groups. A smooth manifold G of dimension n is called a Lie group. if our G is supplied with a structure of a group. First of all, it must be a group compatible with the structure of a smooth manifold, which means that the group operations are smooth. So let me finish this writing. So G, a manifold G of dimension L is called a Flick group if, first of all, G is a group, and second is that group operations are smooth. In other words, a Lie group is a group which is at the same time a smooth manifold, and the group operations are smooth. Now, a physical important example of a Lie group, which you know probably from courses on classical mechanics, is a rotation group. The group of rotational matrices in 3 dimensions is a Lie group. We come a little bit later to the explicit discussion of this group because it is a subgroup of the Lorentz group. And another example, of course, which is primarily important to us, is a Lorentz group. Lorentz group is a Lie group. Now I will try to describe it in more detail. Maybe something of what I will be talking now is already known to you, but maybe something we will find new. Now consider a d-dimensional Minkowski space, R1 d-1, Minkowski space. The Lorentz transformations, by definition, are linear coordinate transformations of Minkowski space of the form x prime mu is equal to lambda mu nu x nu, where again over summation nu, over index nu, there is a summation. And these transformations, these linear transformations of Minkowski space are such that they preserve the interval between 2 events in a Minkowski space. So transformations preserve relativistic interval between 2 events in this Minkowski R1 d-1 space. Now, the infinitesimal relativistic interval ds is defined through the quadratic form. And that's probably you know from the course on special relativity. So eta mu will be Minkowski metric. So eta mu dx nu will be the infinitesimal interval. And the corresponding quadratic form is, if I write it explicitly, is c squared dt squared, where c is the speed of light, minus dx1 squared minus dx2 squared minus dx3 squared. So this is quadratic form, which defines an infinitesimal interval ds between 2 events in a Minkowski space. And so eta mu is Minkowski metric, which is diagonal matrix. So mu and nu are running in general indices 0, 1, 2, and 3. If we are talking about our four-dimensional Minkowski space, and this is 0, which signifies the time direction, and then 1, 2, 3 are indices of the spatial directions. And then Minkowski metric is a diagonal matrix, where on the diagonal you have +1 for the time direction, -1, -1, -1 for spatial directions. And I will adopt this form of metric, Minkowski metric, till the rest of our course. Now, we consider the vector x mu, as a vector. So with components x0, x1, x2, x3, like this.
No.
Yeah.
In this diagonal form, it's +1 and the rest is -1. But in some places it's -1, then it's +1. Means what's the difference between them?
There is no difference. There is no difference. Absolutely no difference. It's just you may use a different convention, and actually in string theory people very often use a different convention when they put here -1, and here they put +1, +1, +1. If you change the notion of the metric, then you have to change the notion of space-like time-like intervals. Then you interchange the notion of what you call space-like and time-like intervals. But there is no principal difference between these two ways of describing the Minkowski metric. It's a convention. In most of the quantum field theory books, people undertaking the convention which I'm using here. Sometimes, and very often in string theory, people are using a different convention for Minkowski metric, indeed. But there is no principal difference. It depends what you call by space-time and, by space-like and time-like intervals. Then the notion of space-like and time-like intervals simply interchanged if we use a different convention to what I'm writing here. Okay? And so this means that if you treat x mu as a vector, in fact, these Lorentz transformations can be written in the matrix form. Very simple. You have a vector x, and it transforms passing from one Lorentz frame into another Lorentz frame simply with matrix lambda, like this. So lambda is a matrix, so lambda is a matrix lambda mu nu, where mu and nu are running 0, 1, 2, 3. And the form of the Lorentz transformations is given by this formula. And the requirement of lambda to preserve the quadratic form is then explicitly written in this way. Eta mu nu, lambda mu, say alpha, lambda nu beta is equal to eta alpha beta. So in other words, Lorentz transformations are transformations which leave our Minkowski metric invariant. Invariance of Minkowski metric. And this defines a class of matrices lambda, which we associate with Lorentz transformations. Now, this transformation here, which preserves our quadratic form, in other words, which preserve Minkowski metric, these transformations can also be written in the matrix form. And this is nothing else as lambda transpose eta. Lambda is equal to eta, where eta we understand as a 4x4 matrix and lambda is a 4x4 matrix. And so in a sense, what you see that this definition here is a generalization of the standard condition lambda transpose lambda is equal to identity, which you know for orthogonal matrices representing the rotation group, right? Now, instead of metric, which is just identity matrix, so +1, +1, +1, +1, you have Minkowski metric. You have Minkowski metric, and this condition here is sometimes can be called pseudo-orthogonality condition, arising from the fact that now you are dealing with Minkowski space rather than with Euclidean d-dimensional space. Now, let us show that matrices which satisfy this condition here form a group. The first statement is that such matrices indeed form a group. And it is clear that as a product in this group, we can just consider the usual product of matrices. And so let's take two matrices, lambda1 and lambda2, which satisfy this condition. So this would be matrix lambda1, and then I take a matrix lambda2.
Hello, Professor.
Yeah.
I have a question. Here, what you tell lambda transpose eta lambda equal to eta. This applies only for the Minkowski space, right? Not for any other general.
No, it's only for Minkowski space. It's only it's a condition which is directly related with the definition of what we mean by Lorentz transformations. Lorentz transformations are transformations which preserve Minkowski metric, and this eta here is Minkowski metric. Okay.
Okay, so it's not for general metrics.
No, this is for this is precisely for Minkowski metric. Minkowski metric, which is a diagonal matrix, and this is what defines for us a class of Lorentz transformations. Would you have a different metric, not Minkowski, but something else? You can still define a group which preserves this metric. In general relativity, or probably also in special relativity, such a group is called a group of isometries. Group of isometries is a group which preserves a given metric. So you may say in this respect that the Lorentz group is simply a group of isometries of Minkowski metric. If you want a different constant metric instead of eta, you can use, if you have a different manifold, not Minkowski space, then you can consider a different space with a different metric and also define a group of isometries in a similar way, which we are doing here. But here we consider Lorentz group, which means the group of isometries of particular metric, namely Minkowski metric. And what I would like to show is that indeed such transformations, which are defined by means of this formula here, they form a group. And so I'm taking two representatives, say two matrices, lambda1 and lambda2, which satisfy each of them this relation. And I'm consider the product of these two. And I need to show that the product lambda1, lambda2 satisfies the same relation, which means that if I take lambda1, lambda2 and take a transpose, and then I put eta and multiply it with lambda1, lambda2, then I will get eta again. Meaning that the product lambda1, lambda2 would satisfy the same defining relation, and so then it would be also a Lorentz transformation. But then it's easy because you see that using the transposition rule, you will get lambda2 transpose, lambda1 transpose, eta lambda1, lambda2. But then you use this relation for lambda1, the defining relation for lambda1, and you get lambda2 transpose eta lambda2. And now you use the defining relation for lambda2, and we know that this is eta And so indeed, the product of two Lorentz transformations is again a Lorentz transformation. Now, identity matrix would be just a trivial Lorentz transformation, which is identity matrix. So it's identity in the group. And finally, we need to show that any lambda has an inverse, which is also a Lorentz transformation. And to this end, you may take and compute the determinant of both sides. So lambda transpose eta lambda will give you determinant of lambda squared multiplied by determinant of eta. It's a determinant of the product of three matrices. And here I'm using the rule that under transposition, the determinant is unchanged. So determinant of lambda transpose eta lambda is a determinant lambda squared multiplied by determinant of eta. But on the other hand, by the definition of Lorentz transformation, this is the same as the determinant of eta. And so determinant of eta is not equal to 0, right? It's actually equal to -1. And so I can cancel it. And so I get from here the condition. The determinant of lambda squared is equal to 1, just to 1. And from here, you conclude that all matrices of Lorentz transformations always have determinant of lambda equals to either +1 or -1. So all matrices of Lorentz transformations have determinant equal to either +1 or -1. But this means that matrix of Lorentz transformation is non-degenerate, and therefore it is invertible. It is invertible. It has an inverse. An inverse is actually easy to find from the defining relation of the Lorentz transformations. You see, if I here multiply this relation by lambda -1 by the inverse matrix of lambda from the right, then I will get lambda transpose eta is equal to eta lambda -1. But then I multiply this relation here by eta from the left. And so I will be getting eta lambda transpose eta is equal to eta squared lambda -1. But eta squared is equal to identity matrix because eta is a diagonal matrix +1 -1 -1 -1 on the diagonal. When you square such a matrix, you get identity. And therefore you get lambda -1. So inverse matrix of a Lorentz transformation is written via the direct matrix as eta lambda transpose eta. And therefore to show that lambda -1 is also a Lorentz transformation, we have to check the following. We have to check that lambda -1 transpose eta lambda -1 is equal to eta. And this we can do by just substituting here this expression for lambda -1. So what we will get is eta lambda transpose eta transpose eta eta lambda transpose eta, like this. And so now using the property of the transposition, we will get eta. By the way, since eta is diagonal, its transpose coincide with itself. So we will get eta lambda eta. Here, eta squared gives us 1 identity matrix, and then we get lambda transpose and eta again. That is what we get. And this is simply eta, because here we have, okay, let me write it maybe explicitly, eta by eta by eta. Eta squared is identity matrix, and therefore the result is eta. And here I use the following statement that lambda eta lambda transpose is equal to eta, which also follows from the defining relation, lambda transpose eta lambda is equal to eta. So this means, in fact, that lambda transpose is also a matrix of Lorentz transformation. So if lambda is a matrix of Lorentz transformation, then lambda transpose is also a matrix of Lorentz transformation. And this you can see again from the same expression for lambda minus 1. Indeed, if you write this expression again, lambda transpose eta, and now multiply it by lambda from the left, then you get here identity matrix, and here you get lambda eta lambda transpose eta, and now you multiply by eta from the right. So you get eta lambda transpose eta squared, but eta squared is identity matrix, and so you get lambda eta lambda transpose is equal to eta. In other words, what I have shown is that if lambda is a Lorentz transformation, then the matrices lambda minus 1, lambda transpose, and lambda transpose even minus 1, they are all matrices of Lorentz transformations. They are also Lorentz transformations. And according to our definition of the group, Lorentz transformations form a group. The usual matrix multiplication is associative. That is, of course, obvious. Very good. And now we can continue investigation of the Lorentz group further. You see that defining relation of the Lorentz group implies the following important statement. Namely, if you take now the condition of preservation of the Lorentz metric, and specify index, the low index of lambdas to be 0, namely the time direction, then on the right hand side you will get, sorry, on the left hand side you will get, because this metric is diagonal, you will get lambda 0, 0 squared, and minus, because spatial directions of eta equal to minus 1, you will get minus lambda eta 0 squared. And on the other hand, this is nothing else as eta 0, 0, according to the defining relation of Lorentz transformation, and this is 1. So from here you see that lambda 0, 0 squared is equal to 1 plus lambda 0 I squared. So lambda 0 I is a vector, and square here means that I'm taking lambda 0 I, lambda 0 I, and I'm summing over I. That is what means square here. And therefore, this is equal. This is equal to lambda 0, 0 squared is equal to 1 plus lambda 0 I squared, which means that this expression here is always bigger or equal to 1, because you are adding to 1 non-negative contribution, lambda 0 I squared. And therefore, from here, you deduce that for any Lorentz transformation, you have two possibilities for the component lambda 0, 0. Either this component or bigger or equal to 1, or lambda 0, 0 is less or equal to minus 1, right? So you have two possibilities. So for any Lorentz transformation, either component lambda 0, 0 is bigger or equal to 1, or such a component is less or equal than minus 1. Now, this has consequence for a topological structure of the Lorentz group. The corresponding Lorentz group, then, well, let me first give a mathematical name for it. It is a six-dimensional non-compact Lie group, whose mathematical name is O1, 3. And this group consists of four topologically separated spaces.
Here, O stands for orthogonal.
Sorry?
O stands for orthogonal.
Pseudo-orthogonal group. That means pseudo-orthogonal group 1, 3. 1, 3 reflects the metric it preserves, and the metric is Minkowski, right? And so if you wish, this is a definition of components. Okay, this is a definition of O1, 3, 1, 3. This is a group consisting of matrices lambda, such that lambda transpose eta lambda is equal to eta. That is the definition of O1, 3. And now these four components are defined in the following way. So you know about Lorentz transformation. Now the following statements. First of all, Lorentz transformations may reverse a direction of time or not reverse the direction of time or keep the direction of time. In other words, they can transform a future point in time-like vector into a past point in one. And the second, so first, reverse or not reverse? Reverse or not reverse the direction of time. The direction of time. In other words, it's related to the fact if lambda 0, 0 for Lorentz transformation is bigger than 1 or equal to 1, or lambda 0, 0 is less or equal to 1, minus 1. Okay. And the second thing is that Lorentz transformation reverse or not reverse, reverse or not reverse the four-dimensional, let's say a four-dimensional reference frame. And this related to the fact if determinant of Lorentz transformation is equal to 1 or determinant lambda is equal to minus 1. Now, Lorentz transformations, which preserve the direction of time, so lambdas for which lambda 0, 0 is bigger or equal to 1, they preserve the direction of time, and for this reason they are called orthochronous. Orthochronous.
Hello, Professor.
Mm-hmm. Yeah.
Here, reversal of our reference frame can be related to the concept like parity transformation or something like that.
Yes, yes, exactly. I'm going to that. Yes, indeed. So you have two operations which are also Lorentz transformations, and these are discrete operations. One of them is parity, and another of them is time reversal. So time reversal will reverse naturally direction of time, and the parity will change the orientation of the frame, and it will transform the matrices with a determinant equal to 1 with two matrices with determinant equal to -1 and vice versa. Now, so lambdas for which lambda 0, 0 is bigger than or equal to 1 are called orthochronous transformations for the reason they preserve the direction of time. And the product of two orthochronous transformations is also an orthochronous transformation. And you can see it easily if you notice the following. So lambda 0, 0 squared, as we said, this is 1 plus lambda I 0 squared, and this is bigger or equal to 1. And this implies that modulus of lambda 0, 0 is bigger than the norm of the vector lambda 0 I. So if you consider now lambda 0 I is a three-dimensional vector where I runs 1, 2, 3, and then lambda 0 I squared is the square of its norm, then it naturally follows from this relation that modulus of lambda 0, 0, which actually lambda 0, 0 itself, if you assume that lambda 0, 0 is positive, so it's bigger or equal to 1, then lambda 0, 0 is bigger than the norm of lambda 0 I. Now, analogously, if you change in this relation lambda to lambda transpose, which is also Lorentz transformation as we have shown, then from here you can deduce that lambda 0, 0 modulus will be bigger than the norm of the vector lambda 0 I, now with a lower index I, than the norm of this vector. Because you are changing lambda to lambda transpose, it means that you are exchanging rows with columns, and therefore you will get another inequality of this type. But now for lambda 0 I with low index I, okay? And therefore, from here, if you consider the product, lambda 0, so you take product of two Lorentz transformations, and then you take 0, 0 component. So I take lambda, and I take another Lorentz transformation. Let's denote it by lambda prime. And now you take out of this 0, 0 component. Then according to the product of matrices, what you would write here? You would write lambda 0, 0, lambda prime 0, 0, plus lambda 0 I, lambda prime I 0, right? It's a standard product of matrices, product of two matrices. So I'm summing over internal index. Once it takes value 0, and another time it takes index I. So it's just the product of matrices here. And now if you use the Cauchy-Bunyakovsky-Schwarz inequality, which essentially tells you that for any two vectors x and y, you have modulus of a scalar product x and y is less or equals the norm of x multiplied by the norm of y. You deduce from this Cauchy-Bunyakovsky-Schwarz inequality is that modulus of the scalar product of these two vectors, lambda 0 I, lambda prime I 0, modulus of this scalar product is less or equal to norm of lambda 0 I multiplied by the norm of lambda I 0, right? That's an application, straightforward application of the Cauchy-Bunyakovsky inequality. And so from here you see, therefore, that the modulus of this term here is less than the product of the norms of these two vectors. And therefore, if you assume that lambda 0, 0 and lambda prime 0, 0 are both positive, from here you conclude that lambda prime 0, 0 is also positive, which means that it must be bigger or equal to 1. Because any Lorentz transformation with positive lambda 0, 0 must have the property that its 0,0 component is bigger or equal to 1. So in other words, if we have two orthochronous transformations, then the product of these two orthochronous transformations is also an orthochronous transformation, which means that orthochronous transformations by itself form a group. You can also show that the inverse of the orthochronous transformation is an orthochronous transformation. And this group or subgroup of the Lorentz group, which consists of orthochronous transformations, it is denoted as O plus 1, 3. And this plus is exactly related to the fact that you consider Lorentz transformations preserving the direction of time. Now, concerning the determinant, the Lorentz transformations which preserve orientation are called proper. Proper transformations are those which preserve orientation. Preserve orientation. And these are transformations. These are transformations with determinant equals to +1. And transformations with determinant equals to -1, they are called improper. And so proper Lorentz transformations, they form a subgroup of the Lorentz group, which is denoted as SO1, 3. And the letter S, as usual, means special. So special orthogonal transformations preserving Minkowski metric, they are called proper Lorentz transformations, and they form a subgroup of general group of Lorentz transformations. And now you can combine these two properties of being orthochronous and being proper. These transformations form a subgroup, which is called a restricted Lorentz group. So restricted Lorentz group, denoted as O plus 1, 3. This is a subgroup of O1, 3. And it consists of proper orthochronous Lorentz transformations. Proper orthochronous Lorentz transformations. Okay, and so proper orthochronous Lorentz transformations, actually identity matrix is a proper orthochronous Lorentz transformation. So identity matrix belongs to this topological component of the Lorentz group. And now I can draw actually the picture of how topologically the Lorentz group looks like. So first, we have a component which consists of all Lorentz transformations, which have a lambda 0, 0 bigger or equal to 1, and which have determinant of lambda equals to 1. And this is our restricted Lorentz group, SO1, 3. Okay, so proper orthochronous Lorentz transformations. Then there is another component which contain lambda 0, 0 is less or equal to -1, and the determinant of lambda is equal to -1. So improper transformations inverting the direction of time. And the passage from restricted Lorentz group to this component is done by application of what is called time reversal. Time reversal is a particular Lorentz transformation which is done by means of the diagonal matrix. diagonal matrix, which looks like -1, 1, 1, 1. So as you see, this matrix change the direction of time because of this -1 here. And on the other hand, if you compute its determinant, you see the determinant is equal to -1. Now, there is another component, which is a component containing matrices with lambda 0, 0, now bigger or equal to 1. So orthochronous transformations, but those which change orientation. For them, determinant of lambda is equal to -1. And this component is obtained from the proper orthochronous subgroup by means of application what is called parity or space inversion. Space inversion denoted by P. And this P is realized also by a diagonal matrix, which is diagonal 1, -1, -1, -1. So this parity changes orientation, if you wish, of the 3 spatial coordinate axes by multiplying them with -1. So orientation of the spatial frame changes to opposite. Now, and finally, it remains to consider another component, I draw it here, of the transformations which are not orthochronous. So they don't preserve the direction of they change the direction of time, but they are proper. So determinant of lambda is equal to 1. And this component is obtained from restricted Lorentz subgroup by means of combined application of a space inversion with a time inversion. Those two do not change the determinant. As you see, this changes the determinant, provides the determinant equals to -1, but this also provides the determinant equals to -1. So combined application keeps the determinant equals to 1, but since our time reversal is employed, then what you will obtain are matrices of non-orthochronous Lorentz transformations. Very good. So discrete operations which relate these topologically distinguished or topologically different components of the Lorentz group, they are the following discrete operations. If I also add up identity, which is simply identity matrix in the group, so this will be P, T, and PT. So these discrete transformations also form what is called a discrete group or discrete subgroup. Discrete subgroup of the Lorentz group for 3,1, which allows the movement among these different topologically different components. Okay, now this picture suggests that only this component here is an actual subgroup. So maybe I will color it a little bit with yellow. So only this component here, which is which are the proper orthochronous Lorentz transformations, they form a subgroup of the Lorentz group. The other components, if you take them by themselves, they do not form a subgroup. None of them forms a subgroup of the Lorentz group. So there is only one subgroup, and this subgroup is a subgroup of proper orthochronous Lorentz transformations, because only this component contains an identity. Group identity sits here in this SO plus 1, 3. Okay, so connected subgroup of the Lorentz group of dimension 6 is this SO plus 1, 3. Now, why dimension 6? Why Lorentz transformations are 6-dimensional? And why they form a 6-dimensional Lorentz, 6-dimensional Lie group? That is because, as you probably know from the courses on special relativity, Lorentz transformations combine 3 rotations around 3 coordinate axes, x, y, and z. And in addition, there are boosts, 3 boosts, which involve 1 spatial direction and 1 time direction, and the time direction. So roughly speaking, if you have a 4-dimensional Minkowski space, like for instance, we draw the direction of time here, x0, and then there are 3 special directions with coordinate x, y, and z. And then there are 3 rotations between this axis, x, y, y, z, and x, z. But also there will be 3 rotations between x0 and one of these 3 axes. So altogether, there are 6 continuous transformations, 6 transformations parameterized by continuous parameters, which is exactly this group of Lorentz transformations. Together, of course, with discrete operations of inversion of space and inversion of time. Now, concerning rotations, I guess you have this in elementary courses on quantum mechanics, how to describe them. And let me just remind that what you can parameterize, how you can parameterize any rotation. You can do it by specifying the rotation axis, say n, and this can be done by specifying a unit vector. So let n be a unit vector, and then you also specify a rotation angle around this direction, around this unit vector, and this will be theta. So you specify rotation by giving an axis of rotation, and this can be parameterized by a unit vector n, and a rotation angle. And so if you define the following 3 by 3 matrices, let's denote them A1 being given by 0, 0, 0, 0, 0, minus 1, 0, 1, 0, A2 given by 0, 0, 1, 0, 0, 0 here, minus 1, 0, 0, and A3 given by 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Then such a transformation is described by a matrix R depending on n and angle theta, which is simply exponential of theta multiplied with a scalar product of n with vector A. And vector A comprises these 3 matrices, A1, A2, A3. So R depending on n and theta is a 3 by 3 matrix of rotations specified by the direction n and the angle theta. You can compute this matrix quite explicitly. In fact, this scalar product n multiplied by A is, if you wish, you can write it as minus epsilon with components. So you take components ij, because matrix, you deal with matrices here. So A is a matrix. So scalar product n by A is a 3 by 3 matrix, and you can specify its ij's component, i's row j's column. It gives you on intersection ij's element, and this element you can easily compute it. It will be given by epsilon ijk multiply with nk sum over k. This is how it will look like. And what you can do, you can compute this exponential explicitly. You can exponentiate this product n multiplied by a multiplied with theta. And this gives you an explicit 3x3 matrix with the following matrix elements. Please do it computation. It's an exercise to do. So R and theta, ij's component of it is equal to cosine theta delta ij plus 1 minus cosine theta ni and j minus sine theta epsilon ijk and k. This is how the ij's component of this 3x3 matrix will look like. You can explicitly check that this matrix is orthogonal, so it satisfies the property that R transpose multiplied by R is the same as R multiplied by R transpose is equal to 1. You can easily check this. Orthogonality relation, which means that this matrix is an element of the group SO3, the group of rotation. It has a unit determinant. What else should be said? The angle theta, originally you may say that you specify rotations by allowing theta to run, say, from minus pi to pi, which covers the whole interval 2 pi. But in fact, you may restrict this rotation angle to run, say, from 0 up to pi, because the negative values of theta from minus pi to 0, they are equivalent to changing the direction of vector n to the opposite. Well, you can easily see it from this formula here. If you change the sign of theta, then cosine of theta will not be changed. Since here you have ni and j, then if you change the sign of all ni's, then this product will not be changed. And here, change of the sign of theta will lead to appearance of plus here, but this plus can be compensated by changing the sign of all nk's. So in other words, rotation by negative angle can be represented by changing the sign of n and allowing theta to still run from 0 to 2 pi, from 0 to pi, okay? So that's why you can restrict theta to run from 0 to pi, but n you will allow to be an identity, to be a unit vector, which actually runs over its endpoint. You may allow to run over the whole two-dimensional sphere. And very often people use this model for a topological description of the rotation group. They say that actually the angle can be identified with the length of this vector, n. So you don't make it unit vector, but you fill actually the ball of a radius pi. Any point inside this ball of radius pi will represent a certain rotation in the direction specified by the line connecting the 0 point with the point inside the ball, and the rotation angle will be given by the length of the interval connecting this point with the origin. And what is a bit non-trivial in this description of the rotations is that opposite points on a sphere, diametrically opposite points on a sphere, should be identified. Because it is a rotation on angle pi and minus pi will actually gives you the one and the same rotation. Well, it's clear from the point of view of usual intuition, if you rotate by pi, it's the same as a rotation by minus pi, so you have to identify these 2 points. So points, diametrically opposite points on the surface of this ball of radius pi should be identified. And this gives a topological model for the rotation group. Now, we know everything about rotation, so it's topologically, it's a ball with opposite points on a sphere on its surface identified. And now we can embed this rotation group into the Lorentz group, and embedding is done in the following way. So from the point of view of the Lorentz group, rotations look as follows. So the time direction is untouched and represented by just 1. And here you have 0, 0, no Lorentz boosts involving time. And here you have this 3 by 3 matrix R depending on n and theta. And so this is the way you embed your rotations into 4 by 4 matrices representing Lorentz transformations. So rotations is a particular example of Lorentz transformations. Obviously, it preserves Minkowski metric because it do not touch time direction, and it preserve the space-like metric, the space components of the metric. Also, you can check about this matrix R that it satisfies the property that if you add up to pi, this will be the same matrix. So R depending on n and theta plus 2 pi is equal to R on n and theta. So periodicity in theta is a property of these transformations. Now we come to boosts. Let me maybe just give one comment, and we will continue in the next lecture. So boosts will be represented also by 3 by 3 matrices. 0, minus 1, minus 1. And all the rest is 0. So 2 zeros here, 2 zeros here, and here is big 0. B2, 0, 0, minus 1, 0, 0. 0, minus 1, 0, 0, and big 0 here. And finally, B3, the third boost is 0. 0 here, 2 zeros here, minus 1, 2 zeros here, minus 1, and again, big 0 here. So there will be 3 matrices, B1, B2, B3, and quite analogously to rotations. Now there will be rotation, but what is called hyperbolic angle. So the corresponding Lorentz transformations are now specified again by the axis around which you rotate and by the rotation angle. They call it var theta. And this is again exponential var theta n multiplied by b. And how this matrix explicitly looks like, we consider on the next lecture. So at this point, I would like to put a dot to stop. And if you have questions, please ask me.
Well, so when we talked about embedding our rotations, so what did we mean by that? And what are we trying to express, or what are we trying to get from this?
What I'm trying to say is that Lorentz transformations is a 6-dimensional Lorentz group. So it contains 3 rotations. Rotations around axis x, y, z. And it also contains Lorentz boosts. And so now I am describing with this kind of a fine structure of how Lorentz transformations look like. Because we said that Lorentz transformations are 4 by 4 matrices which preserve Minkowski metric, right? So lambda are 4x4 matrices, which preserve Minkowski metric. And now I would like to explain how these 4x4 matrices accommodate inside themselves the usual three-dimensional rotations around axis x, y, z, as well as three Lorentz boosts. It means Lorentz transformations, which involve time direction and one of the special directions. And so when I say embedding, I'm describing how three-dimensional rotations, or rotations of this coordinate axis x, y, z among themselves, how they sit inside this 4x4 matrix of general Lorentz transformations. Okay, so this is how they look like, where the rotations sit inside this 4x4 matrices preserving Minkowski metric.
Okay, thank you.
They constitute a part of Lorentz transformations. And this part of Lorentz transformations, which you identify with the usual three-dimensional rotations, they are sitting inside these 4x4 matrices precisely in this way I'm describing here. And in the next lecture, I will explain how to compute this matrix lambda of Lorentz boosts and how Lorentz boosts are embedded in these 4x4 matrices. And Lorentz boosts, of course, as you know from the courses on special relativity, they are parameterized such a parameter as velocity, because boosts means boosting, and boosting means sending something to move with respect to something. And this is what we are moving something with respect to something. We are moving one inertial frame with respect to another with a certain velocity. And this is what is called boost. From the point of view of mathematics, this is a hyperbolic rotation in the plane involving one spatial direction and one time direction. And so this is another type of Lorentz transformations we have to consider. Okay, if you don't have any other questions, then we will meet next Friday and finish with a discussion of Lorentz transformations, also Poincaré transformations, and then come to the discussion of the Noether's theorem. So thank you very much. Thank you very much, and I wish you a pleasant day. Bye-bye.
Bye-bye, thank you.